In this video, I'm just going to go through the answers for the circular motion questions that I set you last week. Okay, so the first one is reasonably straightforward. Okay, it's like a 2D problem, not a 3D problem. So we know that R is 0.4 from the question, and that omega, the angular velocity, is 500 rads per second. And so to find the force, okay, I'm just going to use F equals mr omega squared. Okay, we've got m as well, so my m is 0.7. And so what you've got to do to find the force on the centrifuge, like acting on the ball, whatever it is 0.7 times 0.4 times 500 squared, which is ginormous, is 70,000 newtons. Okay. A centrifuge, you can think of it as sort of like spinning a toilet roll really quickly and something inside is stuck to the walls. It's like a fairground ride, like it, isn't it, where you stick to the walls as it spins around. Okay, then the next question's a bit trickier. So we've got an object hanging on a string that's at 55 degrees to the vertical there, and then it's also going to be 55 degrees there. All right. And then we've got tension in the string. Not very good at this in school. I'm much better doing this pen pad at home. So you've got 55 T acting there, and then we've got the components of that. So you've got T cos 55 acting upwards, and T sine 55 acting inwards. So T55 is the one that's causing the acceleration towards the centre, and T cos 55 is doing the job of balancing the weight of the object. Okay, now we don't know the weight of the object, so all we can put really is 9.8 m. Okay, mg, isn't it, weight? So to solve this, I'm going to have to look at the horizontals and the verticals and then sort of solve to find T. So if we look vertically, because that's going to be easier, there's only two forces vertically, and that is T cos 55 from the string acting upwards, and it must be equal to 9.8 m, which is the weight of the object. Okay, so it's in equilibrium vertically. And we can rearrange that to get that T equals 9.8 m over cos 55. That's going to help later on when I want to solve for T. If we look horizontally then, the formula I'm going to use, or the equation I'm going to use, is F equals mr omega squared. Okay. The length of the string is 1.6, and so the radius of this is 1.6 sine 55, because it's the opposite and the string itself is the hypotenuse. So r is 1.6 sine 55. F is the force towards the centre of the circle, so, and that's T sine 55 from the string, the sine component. So we've got T sine 55 is equal to m, which we don't know, times r, which is 1.6 sine 55, times omega squared. And then if I rearrange that to get T as the subject, okay, well, first of all, the sine 55s will cancel. Okay, there's one from the string there, and there's another one from the radius there. So we've got sine 55 on both sides. And what you end up with is that T is equal to just 1.6 m omega squared. And now I've got two different expressions for T. So I've got an expression for T there, and I've got another expression for T there. So if I equate them to each other, I can take T out. Okay, so I won't actually ever need to know T. And the m's will cancel as well, and we can just be left to find omega. So if we now say that 9.8 m over cos 55 is equal to our 1.6 m omega squared, because they're both t, aren't they? That cancels with that, and now you're just left with one variable, which is omega. So if you do 9.8 over cos 55 and then divide by 1.6, so bring the 1.6 over, you can get that omega squared is 10.67, okay, and then when you square root it, omega is 3.267. Now the question asks us to work out the speed of the particle, which is v. So we've got omega at the minute. It was easier to work with omega at the start. All you do to find v is v equals r omega, and so v equals 1.6 sine 55, that's our r from earlier on, times the 3.267, which is our omega. If you left it on screen for accuracy as well, that'd be good. And v is 4.28 meters per second is the tangential speed, and 3.267 is the angular speed. Okay, so that's not too bad. You can get yourself in a pickle up here if you got on the wrong route, but the easiest way was to make t the subject and then equate these, and then you don't need to worry about t. It just drops out. Okay. The next question then is 3 parts. So initially we've got the string 70 degrees to the vertical, and the string is 0.6 meters long, and your first job is just to prove that it's not touching the surface. So in other words, finding this height here and proving that it's less than 0.3, because it's this point here is 0.3 above the ground. So if I put a 0.3 in there, if 0.6 cos 70 is less than 0.3, then we've proved that it is actually in the air. So 0.6 cos 70 is 0.205 meters. So it's definitely off the surface. So the string is doing all of the work, that means. And then like before, we've got our components for t. Remember, t is actually in the string itself. So we've got t cos 70 acting upwards and t sine 70 towards the center of the rotation. And it's actually like really similar now, because the mass is 0.4. So this time you can work out the weight. So mg is 3.92. So resolving vertically, t cos 70 is equal to 3.92, and from that you can find t. So t comes out as, I mean, accurately it's like 11.4613 blah 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 blah. Okay, 11.5 to 3 significant figures. And then now we know what t is. If we work horizontally, so that was vertically, so working horizontally now, I'm going to use F equals mr omega squared again, because we're supposed to be finding the angular speed, which is omega. So mr omega squared, so that's our 11.46 number. So if you've left it on the screen, sine 70 is equal to 0.4, which is the mass, times 0.6 sine 70, and I'm getting that from the radius here. So that's 0.6 sine 70. So I don't know why that's writing in dotty writing. So 0.6 sine 70 is the radius, and then we've got omega squared on the end. And there's only one unknown, which is omega. So if you just work that through, you should be able to get that omega squared is 47.75, and so omega is 6.91 radians per second. Okay, right, it gets a little bit trickier then. So in the second part of the question, the angle is 60 degrees, and it says the contact force between the particle and the surface is 0. So this time, because we're at 60 degrees, and 0.6 cos 60 is 0.3, so it is on the surface, but it would be in that exact position if the surface was there or not, because even if I removed that, 0.6 cos 60, I don't know why I've put 6 in there, so 0.6 cos 60 is 0.3 whether the surface is there or not. So even though it's touching the surface is not actually doing anything. Okay, there is no contact, like there's no force required between the surface and the particle. Okay, so it's pretty much the same as last time. So we've got 3.92 acting down still. 3.92 acting down. We've got t cos 60 acting up this time, not 70, and t sine 60 acting inwards. The radius this time is 0.6 sine 60, and the calculations are the same. So first of all, working vertically this time, t cos 60 is equal to 3.92, and dividing by cos 60, t comes out as 7.84. And then working horizontally, so in the plane of the circle, so f equals mr omega squared again. So 7.84 sine 60 is equal to 0.4 times 0.6 sine 60 times omega squared, and again we've only got the one unknown, which is omega, so omega squared comes out as 32.6 recurring, and omega comes out as 5.72 radians per second. Okay, and then the third part is different because this time the surface is doing some of the work. So even though the angle is 60 degrees, so it looks the same as last time, but the difference this time is the particle is not going fast enough. So the only reason it's there is because the table is doing some of the upwards work. There's not enough tension in the string this time because omega is 2, and we proved in the last part, look, that for the string to do the work and the table to do nothing, omega needs to be 5.72. So if omega has dropped to 2, then there's not enough tension in the string now to carry the weight of the particle. So we've still got 3.92 down, and we've still got t cos 60 up, but this time we also need the help of some contact force R, because t cos 60 is not going to be enough this time. We've still got t sine 60 acting inwards, and we've still got a radius of 0.6 sine 60. And this time, because we know omega, the maths is slightly different. So I can't resolve vertically because I don't know t and I don't know r. So vertically I can't start there. So let's try working horizontally first because there's only the one unknown, which is t. So the equation I'll use is f equals mr omega squared because I know m, I know r, and this time I do know omega. So the force towards the centre of the circle is t sine 60, and that's equal to 0.4 times 0.6 sine 60, which is the radius, times 2 squared. And if you work out that right hand side, the sine 60s cancel. Okay, or you can just work it out and divide by sine 60, but they cancel anyway. T comes out as 0.96 newtons. And then we can work vertically. So in the vertical direction, we've got t cos 60. So t cos 60 plus r this time, because r is helping to lift the particle up, is equal to the weight, which is 3.92. So 0.96 cos 60 plus r equals 3.92, and if you take away the 0.96 cos 60, you get r is 3.44 newtons. So actually, out of the total weight of 3.92 newtons, the table, the surface, whatever it's on, is actually doing most of the lifting, and the string is doing barely any. The string is doing what, half a newton of lifting, because we just don't have the angular velocity to give the tension in the string that we need. Okay, so if we remove the table this time, the ball would actually drop to an angle that's not 60 degrees. It would find like a new angle that does work with an omega of 2, but it wouldn't be 60 if we didn't have the table. And then the last question, so this time we've got two strings attached to a ball of mass 0.05, okay, and we've got a V of 5. So if I'll just sort of shrink this down to what's actually important. So M is 0.05, and then mg, the weight from that, if you work it out, is 0.49, so it like times in by 9.8. We've got a V of 5, and we've got a radius of 1.2, so that was given to us in the question. The angles are both 55 degrees, so 55 and 55. And we've got two different tensions, so find the tensions in the strings. It's not the same string looped through, it's two different strings, and one has got more tension, more newtons than the other. So we've definitely got a 0.49 newtons acting downwards. Now what I'm going to do for those strings is I'm going to call them T1 and T2 because there's two different tensions. So if I say the top one is T1 and the bottom one, dearie me, the bottom one is T2. And we've got the angle 55, so acting upwards is the cos component of T1, so T1 cos 55, and acting in towards the centre is T1 sine 55, so that's the T1 sorted out. T2 is pulling downwards, so we've got a downwards component of T2 cos 55, and we've got a sort of towards the centre component T2 sine 55. So the sine components are working together to pull the ball towards the centre, but the cos components are acting opposite to each other because the bottom string is pulling the ball down and the top string is pulling the ball up. And just from that I can tell you that T1 is going to be bigger because T2 cos 55 plus the weight of the object is equal to T1 cos 55. So I know already that T1 is doing most of the work here. There's more newtons of tension in T1 than there is in T2. And you're going to need simultaneous equations. So we're going to have to work vertically and horizontally and then try and equate them or put one into the other. So working vertically, T1 cos 55 is on its own acting upwards, and that must be equal to T2 cos 55 plus the 0.49. Okay, and then working horizontally, so I'll leave a bit of space, working horizontally, so F equals mv squared over r I'm going to use this time because we've got v, so I'm going to use this version of the formula for F. Remember, F is the force towards the centre, and we've got two of them this time, so it's both of these added together because they're working together. So that gives us T1 sine 55 plus T2 sine 55 is equal to mv squared over r, so 0.05 is m, 5 squared is the v squared bit, and r is 1.2. Right, so I've got two equations with two unknowns, T1 and T2. Easiest way to sort that out is to make either T1 or T2 the subject and then dump it into the other one. So what I'm going to do up here, I'll make T1 the subject. It's not going to look particularly pretty, so T2 cos 55 plus 0.49 and then all divided by cos 55. You could tidy that up a bit, can you, cancelling through cos 55. So maybe it's a bit neater if we said that that's just T2 on its own plus 0.49 over cos 55. So maybe that's a bit tidier for substituting in. So if I substitute that into here, where we've got T1. That's going to give us, so all this is going to have to go into brackets. So sine 55 is going to need to go at the front. So sine 55 brackets and then T1. So T1 is T2 plus 0.49 over cos 55 plus T2 sine 55 on the left as well, isn't it? And that's all equal to, and if you type it into a calculator, it comes out as 25 over 24. That's probably the neatest way of writing it for now. Okay, expanding all of this, you get T2 sine 55 plus sine 55 times all of this. So I'm multiplying them together, which actually just comes out as 0.7. And then we've got plus T2 sine 55 equals 25 over 24. It's just sort of working your algebra through now. If we take away the 0.7, okay, calculator would do most of the work here. As a fraction is 41 over 120. I didn't bother converting to a decimal because I knew it would be horrible. And then on the right now, we've got T2 sine 55 plus another T2 sine 55. So that's 2 T2 sine 55. Okay. If you divide by 2 sine 55, you get that T2 is 0.209 newtons. Okay. All you've got to do then, look, to work out T1 is to substitute it back into there. Alright, and T1 comes out as 1.06 newtons, which proves what we said at the beginning, that T1 would need to be bigger than T2, because T1 cos 55 acting upwards on its own is equal to T2 cos 55 plus 0.49. Okay.